The topic of today's lecture is to start answering some of the questions that we raised during the previous lecture when we defined the framework for supervised learning. And specifically, what I want to do in this lecture, I want to introduce you to a notion that's very central to theoretical statistical learning, which is the notion of probably approximately correct learnability. So it's a mouthful, and we'll spend some time building up to that definition to understand and appreciate what it's telling us. We will really only define that specific concept at the very end of the lecture. We're going to take a very pragmatic route because I want to motivate why such complicated and sometimes obscure mathematical definition actually makes sense from a very practical perspective. What we're going to do, we're going to take a view of a slightly simpler supervised learning problem in the sense that we're not going to consider the most general framework that we established during the last lecture. What we're going to do is consider a special case that is a little bit easier to manipulate, although I will have you in the homework make sure that actually we can go back to the original framework and study this in full generality. It's going to be a special case in the following sense. We're still going to consider a data set, x1, y1, xn, yn, that consists of feature vectors, the xi's, associated with their labels, the yi's. The xi's are going to be drawn RID according to an unknown distribution px. And just as a little word on notation, the notation here that I'm using is not the one that is super standard in probability. That's one that's pretty common in statistics, pretty common in machine learning. I want to draw your attention on the following so that there is no ambiguity regarding notation. When I write px here, what do I mean? Px here, you want to think about it either as a PMF, a probability mass function, if it happens that the alphabet x over which you take the feature vectors is such that it is finite. Okay, so a good example of that is if your feature vector is comprised of statistical data which is categorical, your zip code, the number of people in your family. But I will also use it a little bit informally and with a slight abuse of notation if you have a PDF. Okay, so in that case, if x is such that the cardinality of x is infinite, and typically the example that we have of this is when we take x to be the entire real line. Okay, so it will be a slight abuse of notation. The second thing I want to emphasize is that the subscript that I use, this bold x, is what I use as a reminder that we're taking the probability over x viewed as a random variable. The one thing I'm not doing very carefully is that I typically don't distinguish between the random variable and its realizations in terms of notation. The context should make very clear what we're doing, and I'm usually very careful, but the notation, because I didn't want to have too many complicated notation, is not making that distinction. So if you ever have a doubt as to what is the quantity I'm manipulating, what is random, what is not random, ask me to clarify. But I'll do every effort to be extremely clear to avoid any misunderstanding. This is the assumption we did last time. The one simplification we're going to do is we're going to assume that we have a binary classification problem. So to every feature vector, we associate a label that takes values in 0, 1. The other simplification that we're making is that the labels are actually correct. There is absolutely no error in that definition here. There is no error on the label. And it corresponds to a special case where the unknown distribution py given x that we had introduced last time is actually error-free. There is no noise introduced in the system. Okay? No noise. So we're really trying to learn a function. We're going to also assume that the class of hypotheses that we're going to be looking at is actually finite. What that means is that the cardinality of H, the hypothesis class that we use to come up with models that can explain the unknown function f, has a finite cardinality that I called capital M. And to make my life easier, I'm also going to write all the functions H, or all the hypotheses H, in my calligraphic set H as HI, and I'm going to number them from I equal 1 to capital M. So this is just notation, but that's going to make my life a little bit easier. The next simplification I'm going to do, coming from the very general model that we introduced on the previous lecture, I'm going to talk about a binary loss function. So I'm not going to take any arbitrary loss function. I'm going to focus on the binary loss function that is quite simple. Because I know that my labels are binary, all I'm going to do is I'm going to have a loss function that outputs 1 if the labels are different, and 0 if the labels are the same. Okay, so again, to avoid any ambiguity as to what I'm doing, what this is saying here is that this is saying that my loss function is going to be 1 if you're comparing two labels that are different, and it's going to be equal to 0 if you're comparing two labels that are the same. So in other words, what you're doing is you're penalizing by 1 every time you make a prediction error, and you penalize by 0 otherwise. So what's important here to notice is that that simplification allows me to simplify the notion of risk. You remember from the last lecture, we introduced the notion of empirical risk and the notion of true risk. What the simplification of using a binary loss function allows us to do is that we can now replace the risk by a probability. As you will see in the next homework, this is not a huge loss of generality because you can extend everything I'm going to do today in class to the general case. But I think conceptually, as a first exposition to PAC learnability, it's much easier if you feel that you're dealing with probabilities as opposed to dealing with a general risk function. Let's go over what I'm writing here. What I'm claiming here is I'm claiming that the risk R of H, so the true risk, which is defined as the expected value over X and Y of the loss function, turns out to be just the probability that when you predict H of X, you don't get Y. Where does that come from? It comes from exactly the definition, and I'm going to write it explicitly. So if you look at the definition of the expectation, in principle, it's going to be the sum over X, the sum over Y, of the probability of X, the probability of Y given X, of Y given X, of the indicator function, which says H of X not equal to Y. And by definition of the indicator function, we know that this is 0 whenever H of X is equal to Y. So what you end up doing here is you merely end up summing all X and Y over all the pairs X and Y such that H of X is not equal to Y. And what are you summing? You're summing the joint distribution, essentially Pxy of X and Y. And that, by definition, is what I call the probability over my random variables X and Y of H of X not equal to Y. So this is in part the reason why I introduced that proposition in my lecture notes on probability, because we already see it in action here. So that simplification will make our life a little bit easier, because analyzing the risk R of H will boil down to analyzing a probability. Again, just a technical simplification. You will explore in the homework how to generalize that. The other thing that you can notice is that the empirical risk becomes quite simple too. If you substitute the loss function, the binary loss function that we are using here for the general loss function in the general definition of the empirical risk, you see that your empirical risk is just an average of indicator functions. So that's the model that we're going to use.